Hello and welcome to the course of Advanced Strength of Material. In this course, we are dealing with the advanced topic of the strength of material. Strength of material we have studied in the first year. Till now, we have seen about strain energy, and after the strain energy, we have start a new module called pure bending or bending and shear stress in beams. So in the bending we have already seen what is pure bending, what is the bending equation, and what is the simple bending. These three things we have already seen. Now in this lecture we will see about in this lecture, this is the second lecture of module 2 and fifth lecture all total. And in this lecture we will see about assumptions of theory of bending, moment of resistance, and about section modulus. So we will see what is the value of what are the assumptions. So the lecture objectives are to understand about the assumptions that are made for theory of bending, next to introspect about the moment of inertia, and thirdly to get an insight about section modulus, means what is section modulus and what is its definition and what is its significance. This we will see. And let's start our lecture. So what are the assumptions made? First assumptions are material should be homogeneous. Homogeneous means the beam material should be similar, should be made of a single kind. So that means the beam should be made of similar kind of a material. That only then we can apply the theory of pure bending. So this is our first assumption, that is material should be homogeneous. Second assumption is the material should be isotropic. That means the material should be isotropic means the elastic property or the property of the material should be independent of direction. That means it should be independent of direction. That means there is no direction dependency. That means the material, the property will be same when all over the or throughout the material. The property value of the property will be same throughout the material. So this is the example, this is called isotropic. And next, the value of Young's modulus. See, value of Young's modulus for tension and compression should be same. So the material should be like that, so that the value of the material, the value of the compression, Young's modulus in compression or in tension will be same. Fourth one is transverse section. This is important. That is transverse section before bending. Transverse section which is plane before bending should remain plane after bending. That means what is transverse section? See here. This is the workpiece. This is our piece or this is our beam, and this is its neutral axis that we have studied earlier. And after bending, what will happen? After bending, the bending will look like this. The bending will look like this. So now this is the transverse section. This section is transverse section. This section is plane, and this should remain plane to this is one important assumption. This section is this, and this section should remain plane after bending also. So this is the assumptions. And next we will see some more assumptions, such as the beam is initially straight and all the longitudinal filament should bend into a circular arc with a common radius center of curvature. That means each and every fiber of the beam should be each and every filament of the each and every longitudinal filament should bend into circle with arc or circular arc with a common radius of with a common center of curvature. Okay, so center of curvature should be common. Next is the radius of curvature. The radius of curvature is large compared to the width or compared to the dimension of the cross section. If the dimension of the cross section is because the dimension of the cross section is very small as compared to the radius of the curvature, and each layer of the beam is free to expand or contract. It is independently and last assumption is each layer of the beam is free to expand or contract independently. That means the layer below and above the neutral axis should easily be contracted or expanded depending upon the type of load or and that is our depending upon the type of load and the position, and they are free to expand. They are independent. That contraction and the expansion is completely independent process. So it is a completely independent process. So that's why the last term is said that each layer of the beam is free to expand or contract independently of the layer below or above it. Means they do not care about the layer below and above it. They only care about the bending of its own filament. So each and every layer, the filaments are independent to bend or to expand or contract. So that's it. These are the assumptions. Now we will see about our moment of resistance. But before that, consider a bar ABAC. Now in that bar, this is neutral axis, NN is the neutral axis. Now a fiber that is at y distance from the neutral axis is E into F, and the original length is BX. Now original length is dx. Now if we bend this material, the material will be bent at the center of radius R, center of curvature R, taking center of curvature R. When we take the center of curvature as R, this center of curvature is measured, this R is measured up to neutral axis. This is using due to our simple theory of bending. And now we can calculate the strain. How the strain can be calculated? Strain is equal to change in length to the original length. Now change in length is equal to y into theta, and original length is r theta. So that gives us y by r. So strain is equal to y by r. Similarly, stress can be found out by epsilon into r. Stress can be found out by E or Young's modulus into R into strain. So that would give us Young's modulus into stress. So that would give us Young's modulus is equal to stress by strain, and that stress is sigma, and strain is y by r. So now elastic E is equal to our our sigma by y is equal to E by r, or sigma, that is our shear stress. Sigma is equal to E by r into y. So these are the values this is the value of bending stress. Now after finding out stress and strain, we should know about moment of resistance. So see, understand what is happening when we apply force, or bending moment to a body. What will happen? The bending moment or force will generate a deformation. That deformation will be resisted by the material. And for that resistance, a stress will be generated. Due to that stress, a force is generated. Due to that stress, the force is generated, and that force can have moment. That force can have a moment. The total force can have force can create a moment about can create a moment about Na, and this moment is known as moment of resistance. Now, for calculating moment of resistance, from the definition we can see that the moment of resistance is calculated by measuring the force on the length, that is stress by into area, that is given by E into R, E by R into Y into dA. Now moment of the force is force into distance, that E by R Y dA into Y, that would give us E by R Y square into dA. Now for the full place, total number of resistance is given by M is equal to E by R integration Y square dA. Now y square dA is equal to second moment of inertia, or moment of inertia. The moment of inertia and the moment of resilience, moment of inertia and the moment of resistance will be same with moment of inertia and the moment. See, this is equal to y square integration y square dA is equal to moment of inertia, and the moment of resistance will be same with the bending moment, and that's why it resists the bending moment, or it resists the rotation. And so M is written by M is equal to E by R into I, so that would give us M by I is equal to E by R. So if we put sigma by Y in place of E by R, and if we equate them, then we got M by I is equal to E by R is equal to sigma by Y. So this is the moment of resistance, and this is the moment equation. This equation we have delivered, this single equation we have delivered in our previous lecture. Now this is how this equation is been generated. This is not the derivation, this is the derivation how this equation has been generated. So that's it. And now section modulus. What is section modulus? It is defined as the ratio of moment of inertia of a section about NA about neutral axis So it is defined as the ratio of moment of inertia of a section about neutral axis and to the distance of outermost layer from neutral axis, and it is denoted by Z, and mathematically it is given by I, that is moment of inertia, by y max. So z is equal to I by y max. Now this is the formula of section modulus. In the next lecture we will see about how to find out the section modulus of various shapes. So now here as we know that m by I is equal to sigma by y. Now stress will be maximum when y is maximum, so m by y is equal to del max by y max. So that would give us that would give us, so m by I is equal to sigma max by y max. That would give us I, m is equal to I sigma max by y max. That would give us I by y max, give us z, that is z sigma max. So moment of resistance is offered by the section which is maximum when the section modulus is maximum. Hence the section modulus represent the strength of a section. So that's it. Thank you for being here, and I guess you enjoyed this lecture, and if you have any problem, please feel free to contact with me. Thank you.